Before we speak about stability of second-order linear systems, let's recall the first-order linear systems. We said we look at the parameter a, and if a is positive, then graph of x is diverging, and then we say system is unstable. If a is negative, then graph of x is converging and system is stable. Now let's look at the second order linear systems. It can be written in this form or in matrix form, and the question is how to determine whether the system is stable without solving the differential equation, like we did in the case of the first order linear system. And a key concept and the answer for this is study characteristic polynomial and eigenvalues of the matrix A. Let's look at the cases we can have here. First case, when the system is stable. It is stable if both eigenvalues are real and negative numbers, or both eigenvalues are complex numbers conjugate to each other with negative real parts. Second case, the system is marginally stable, and often we can consider that this system is unstable, especially in engineering. System is marginally stable if one of the eigenvalues is negative real number and another is zero, or both eigenvalues are complex numbers conjugate to each other with zero real parts. Third case, when the system is unstable. System is unstable if at least one of the eigenvalues is real and positive, or we have both eigenvalues are complex numbers conjugate to each other with positive real parts. Let's look at the examples generated using Octave software. For stable systems, we have the following. Case 1a, when both eigenvalues are real and negative. Case 1b, when eigenvalues are complex numbers whose real parts are negative. We see in both cases we have blue curves and red curves converging. Second case, when system is marginally stable. We can have the case 2a when one eigenvalue is negative and another is zero. And we see here different initial conditions. But in both cases, we see the behavior of the system is converging. So the lines blue and red, they are converging to some of the values. The problem is that they will always converge to different numbers depending on the initial conditions. Next case, case 2b, when both eigenvalues are complex numbers and their real parts are zeros. And we see we have the oscillations around around zero or another number, and problem is that again, depending on initial conditions, the behavior will be different. And then the last case, when system is unstable. Here we see the diagrams. Case 3a, when one eigenvalue is positive real number and case 3b, when we have both eigenvalues with positive real parts. If you notice, you can see in the case 3b we have kind of oscillations here. We start with very small oscillation and then continue with the bigger, but the oscillations tell us that we have complex eigenvalues. Let's solve the following example. We need to determine whether the following system is stable. Let's find the eigenvalues. Matrix A is the following: 1, 2, minus 3, minus 3. So this matrix, identity minus lambda times A, we need to take the determinant of this matrix. So this will be 1 minus lambda, 2 minus 3, and minus 3 minus lambda. And let's continue. So this will be minus, and then 1 minus lambda, 3 plus lambda, and plus 6. If we expand the expressions in the brackets, we will have minus lambda squared plus 2 lambda and minus 3 plus 6. So finally minus lambda squared plus 2 lambda plus 3. And now we need to equalize it to 0. So if we solve this equation, we will find the eigenvalues. So if we equalize it to 0, this is the same as lambda squared minus 2 lambda minus 3. And if we factor this, we will have the following: lambda minus 3 and lambda plus 1. So we have the following eigenvalues. First lambda is 3 and second lambda is minus 1. We see that one of the eigenvalues is negative real number, which means that our system is unstable.